Hello, we're the team David Scott from the group 322 and we're going to present our evidence of learning of stage 4. We are confirmed by Luis Flores, Alan Puente, Joshua Heldaí, Jesus Robles and Jair Gonzalo. There are three physical laws called laws of Newton. These neurons are considered the most important physical laws about movement. The first one states that every object will remain at rest or uniform static motion until an external force acts on this object. Until then, the object will remain at rest. The second Newton's law states that force is equal to mass times acceleration. And the last one, it states that every force applied on an object or anywhere, it's gonna be in another one in opposite way from equal magnitude but in opposite way. This law is called action-reaction law.
In the second part of the introduction, I'm going to talk about static. Static studies the equilibrium conditions of bodies subjected to various forces. Static is the part of physics that studies the bodies on which force and moments act whose results are zero, so that they remain at rest or in an accelerated motion. The purpose of static is to determine the resulting force and the resulting moment of all the force acting on a body in order to establish its equilibrium conditions. As we know, the resultant force is the one that produces the same effect as a system of force acting together, so the resultant force is equal to zero. In static, the word reaction is often used when talking about bodies in equilibrium.
Hello, my name is Ernesto and I am going to show the free body diagram that is from this laboratory practice. I don't have a board to show it to you, so I'll show it in a notebook. Okay, so in the laboratory practice we have an object that is a bottle filled with sand that is attached to two strings, sorry. So basically there are actually acting four forces in it. There are its weight, both tensions of the strings, and the normal force that exists to cancel the weight. But actually these both forces can be separated in another two forces. There are the tension in X and tension in Y, and actually that also happens in the tension too. What is particular in this free body diagram is that both tensions are at an angle of 45 degrees. In total we have six force acting on this object. And that's all about this free body.
For the calculations, first we calculate the weight, that is the gravity multiplying the mass. The mass of the object is 500 and the gravity is 9.8. So the result is 4,900. The summatorial forces in Y and the summatorial forces in X are zero. So the tensions are equal. And the tension on y and the tension on x will be equal because it's the same degree of inclination. So the tension one is the gravity multiplying the grams that they support, that is 300. So it's 9.8 multiplying 300, that is 2,940 newtons for both tensions. And the tension in one is multiplying the sine of 45 degrees, that is our degree of inclination, multiplying the tension. And this will give us 2,078.9 newtons. And for the tension on x is the same because sine of 45 and cosine of 45 is the same value. And in order to obtain normal force, we isolate from the equation and will let us that the weight minus tension 1 and y minus tension 2 and y will give us 742.2 newtons.
Well, my part is this, to transform newtons to dynas. 1 newton is equal to 100,000 dynas, like 294 millions dynas is equal to T1 and T2. Here we have T1 in X is equal to T2 in X, that is equal to 2078.9 newtons, and we will transform to the dynas. Here this will be 207,000 207 millions 1890,000 dynas, and the weight is 1,900, and this will be like will be 49 millions dynas, and the normal force will be transformed to dynas. Okay. These are the number of 74,220,000 dynas. These are the results in dynas.
Well, as we can see, the results that we get is there in tension 1 and tension 2, the amount of dynas are the same, but if we compare the dynas in tension 1 and 2 with the dynas of the normal force or with the dynas of the weight, we can see that the amount of dynas is different in these two, and it's also different in the other two. And why is this? Okay, all these thanks to that 1 newton is equal to 100,000 dynas. So, for example, imagine we have force of 28 newtons. Okay, if we convert these to dynas, we can say that in total there are 2,080,000 dynas. So this is an example. The value doesn't change a lot. So this is why the tension 1 and tension 2 are the same, because the force was also the same.